This is example 17-4 from Shigley's 10th edition. A 10 horsepower split phase motor running at 1750 revolutions per minute is used to drive a rotary pump which operates 24 hours per day. An engineer has specified a 7.4-inch small sheave and an 11-inch large sheave and 3 B112 belts. The service factor of 1.2 is augmented by 0.1 because of the continuous duty requirement. Analyze the drive and estimate the belt life in passes and hours, assuming a coefficient of friction F equals 0.5123. You see here an image of a motor with a small sheave and a large sheave. So let's look at the givens from the problem. What we know. We know we have a 10 horsepower nominal power motor. We have a 1,750 RPM small sheave. We have the diameter of the small sheave is 7.4 inches. And for the large sheave is 11 inches. The belt is heavy duty type B belt, B112 specifically, where the 112 indicates the nominal belt length. The number of belts is 3. Service factor, K sub S, is 1.2 plus the additional 0.1 because of the continuous duty requirement, giving us a service factor of 1.3. The coefficient of friction was given as 0.5123, so we need to calculate the belt life in terms of number of passes and in terms of lifetime in terms of hours. Here's a variety of different belts. You see the top row here is light duty belts. The amount of horsepower that each one of those can handle is annotated, about 1.5 horsepower for the 3L and less than 7 horsepower for the 5L. And then the second row is the type of belt that we have in our problem, a classical heavy duty belt. And you see the horsepower is less than 13 horsepower. So you see that the second row has quite a bit higher horsepower, even for the smallest belt, than the first row. Then type B, which is of interest to this problem, is less than 25 horsepower. Type C is less than 60. Type D is less than 150, and type E less than 300. And if you look at the first row, the light duty belts are optimal at about 2,000 to 3,000 feet per minute, and the heavy duty belts can run at a higher velocity, 4,000 to 5,000 feet per minute. So we're first going to obtain some geometric parameters from the givens. First off, to specify a V belt, given the belt selection letter, which is the B, followed by the inside circumference in inches, that's the 112. So the calculations involving the belt length are usually based on pitch length. In a given belt section, the pitch length is obtained by adding a quantity to the inside. So we get that quantity from table 1711. And for the B belts, the quantity to be added, the L sub C, is 1.8 inches. At the pitch location, the pitch length is L sub P equals L, the 112 inches, the nominal length, plus L sub C, so that's 112 plus 1.8, which is 113.8. Peripheral speed, velocity equals pi dn, and we have to be consistent. If we use the diameter for the small sheave, we also have to use the rotation speed for the small sheave. And then center distance is calculated using an equation derived from the Pythagorean theorem and other geometric constants. And then the wrap angle, phi or phi, equals theta. And here in this case, we're looking at the wrap angle for the small sheave, and you have the equation for the small sheave using the inverse sign there. So in our example, we have most of these values. We have the small diameter, 7.4 inches, the RPM of the small sheave, 1750 RPM. So we multiply pi times 7.4 inches per revolution, because that's circumference, diameter times pi. In each revolution, it's going all the way around. And then 1750 RPM. And then we've got to convert inches to feet, because the diameter of the sheave was given in inches, and so we want to end up with feet. So we have 1 foot per 12 inches, and that gives us 3,390 feet per minute for our V velocity or peripheral speed. Then the center distance, we have the pitch of the belt, 113.8, and we plug in the large and small sheave diameters, both in 3 places, and we get the value 42.4 inches for the center distance. And then the wrap angle, plug in the large and small sheave sizes and the center distance, and you get the amount of wrap angle in radians. And we have to keep it in radians because we're going to need that later on. The next step is to calculate the allowable power, design power, the number of belts that we need, and the resulting safety factor. when we apply the appropriate number of belts. Now we're going to have to use some tables here. And firstly, we have the horsepower ratings of standard V belts. They depend on manufacturer. In some cases, the basis could be a number of hours or a number of passes. And so we see here in table 1712 from Shigley's for heavy-duty belts A, B, C, D, and E, the different diameters that those are relevant for, and the amount of power that each belt is rated for at a given velocity. Two other tables give us some constants or some correction factors, because the rating in the previous table comes from belts running on sheaves that are the exact same size. And obviously in most systems where we need a belt, the two sheaves are going to be different sizes. We either want to speed up the rotation speed and reduce the torque, or slow down the rotation speed and increase the torque. And that's usually what we're going to do, so that they'll usually have two different sizes. So deviations from those conditions take additional adjustments. So you have K1, which is a correction factor for the angle of wrap in table 17.3, you see on the left hand side. And then you have K sub 2 is the correction factor for belt length. So let's apply these to our example. We're looking at all three of these tables at once. We're going to use table 1712 on the right, then table 1713, and then table 17.4. We have to start by interpolating to obtain the horsepower rating for a belt that's moving at 3390 feet per minute. So that's between 3,000 and 4,000. So we interpolate for the sheave diameter that is greater than 7 inches, and 3390 is 39% of the way between 3,000 and 4,000. So you can take the difference between 5.01 and 4.49, and then take 39% of that difference and add it to the 4.49 to get 4.693. Do that interpolation. Now we're ready to obtain the value for K2, the belt length correction factor, from table 1714. Now you got to watch out on this table because it's organized differently than table 1712 that we just got done with for the horsepower ratings for the different V belts. Look at table 12. Different types of belts, A, B, C, D, E, are arranged horizontally. Now in table 1714, in the middle, belts A, B, C, D are arranged vertically. And you read the K2, the length factor, from the first column, the left side column. So we find our B belt with the appropriate amount of length. Ours was between 105 and 120 inches. Specifically, I think it was 113.8. And so that gives us our K2 value. Finally, we obtain the K1 value, which is the angle of contact correction factor. We have to use that because our two sheaves are two different sizes. And there's two ways to read that table. On the far left, you have D minus D, so the size difference between the two divided by the center distance, or theta, the angle of wrap, which we've already calculated. We got it in radians, convert that to degrees. 3.057 radians is 175 degrees, and so that gives us a K1 value for V and VV belts. So ours is a V-shaped belt of 0.99. So that's not going to make a big difference. It's because our sheaves are not immensely different in size from one another. Now we have the allowable power per belt, and we need to calculate the design power from the motor and a couple of different factors. So we start with design power H sub D equals H sub NOM, which is the nominal motor power, times K sub S, the service factor, and N sub D, and we've been given both of those. And the number of belts N sub B should be the next higher integer. Obviously, you cannot have half a belt. So it's either 1, 2, 3, 4, etc. The next higher integer to that ratio, HD over HA. Then we can rearrange that equation to calculate the factor of safety based on the integer number of belts that we have. In our example, we have a design power of 10 horsepower nominal times the K sub S, which is 1.3, times a design factor of 1, and that gives us 13 horsepower. And then we have the number of belts, which has to be greater than HD over HA. So that's 13 over 4.878, which is 2.675. I can't have 0.675 of a belt, so I need 3 belts. Now we rearrange that equation algebraically to find our factor of safety. So we have the allowable over the design. So HA times the number of belts over H nominal times Ks, and that gives us 0.878 times 3 divided by 10 times 1.3, so that's 13 divided by 13, and that's 1.13. That's our factor of safety for these belts. The next thing we need to do is a series of force balances to find a variety of the forces or tension. That's the same meaning when you're talking about belts, and we'll find the force and tension in several locations. The first force we want to calculate is the tension due to the belt wanting to fly off as the pulley is rotating. So the faster it rotates, the more that inertia is making the belt want to fly off, and that's counterproductive or detrimental to the friction that we need to hold that belt on the pulley. And so that can be considered a loss. And it's related to the velocity. It's related F sub C, so the centrifugal force or tension on the belt equals a K sub C factor that we get from the table that you see there, table 1716, times the quantity V over 1000 squared, and that can only be in feet per minute. Secondly, the force difference between the tight side and the slack side due to transmitted power, delta F equals F1 minus F2 equals 63,025. That's a conversion factor for the units of the design horsepower divided by the number of belts, divided by the RPM, and D over 2. Next, the tight side tension, F1, equals FC times that force difference times the quantity exponent of the friction and the wrap angle on the small sheave, divided by that same quantity, exponent, friction, wrap angle, minus 1. Then the slack side tension, F sub 2 equals F1 minus delta F. You can play with the algebra there and see what's going on, but we need to get these one at a time so that we keep having one equation and one unknown as we go through each step. And then the initial tension, which is the tension prior to startup, is going to be the average of tight and slack side during operation, but it also needs to disclude or subtract the centrifugal tension. Now, if we find those 5 force values, we will have what we need to do the final calculations for the life or number of passes for this belt. For our example, the centrifugal force is going to be Kc from the table, A, B, C, D, E, different types of belts. We got a B-type belt. You get the Kc value 0.965. You plug that in as the constant in the equation. Our velocity was 3390 feet per minute. We square that, and we get 11.1 pounds force due to that velocity, centrifugal force. The bigger that belt, the higher that centrifugal force is going to be. You can see how that works with those K sub C values as you go from an A, B, C to the big belts, the D and the E belts. Then the force calculated from the power, the second bullet point, we've got our conversion factor, 63,025 RPM pound inches per horsepower. We have 13 horsepower divided by 3 belts. That's at 1750 RPM, and multiply that by 7.4 inches divided by 2 in the denominator there, and we get 42.2 pounds force. Tight side tension, F1 equals 11.1. That was our F sub C plus 42.2, and then we have to account for friction using the exponent, 0.5123 times 3.057. That's the amount of radians. Has to be radians, can't do degrees. So that's the number of radians for the wrap angle on the small sheave, divided by that same exponent minus 1. So you get 11.1 plus 42.2 times 4.788 divided by 3.788, and you get a tight side tension of 64.4 pounds force. Now you know if that tight side tension, your calculation result, is lower than the delta F, you know you have a problem, because you're going to end up with a negative value in there, and you can't have a negative value of tension on a belt. So then we calculate the slack side tension, F sub 2 equals that difference between the tight side tension and the force difference, the delta F, so 64.4 minus 42.2, and on the slack side we only have 22.2 pounds force. And then the initial tension is going to be the average of F1 and F2 minus that centrifugal force, because when we start it up we don't have any centrifugal force, so we have to subtract that centrifugal force from the average, and we get 32.2 pounds force initial tension. So that initial tension is going to be the same on the tight side and the slack side because it's initial it hasn't started up yet. It's not pulling, it's not producing torque through that belt yet. So now we have our 5 different values of force. Now we're ready to calculate the life in terms of number of passes or number of hours for this belt. Life calculations can be complicated for V-belts because if you think about the pulley, there's a significant amount of distance above the pulley as the belt is going around that it has to flex. So the inside of the belt is going to be under compression and the outside is going to be under much higher tension as it's going around. It has to be longer as it's going around the sheave. So that lengthening is adding force, is adding significant tension, and that's calculated for both the small sheave, the driving sheave, and the large sheave. And the way to calculate that is using the parameter K sub B in table 1716. And so you see that the tension at the small sheave side is tight side tension F1 plus KB over D, little d, the small sheave size, and then tension at the large sheave is F1, tight side tension, plus that same constant K sub B over the big D, the large sheave diameter. Let's jump down to equation 17-27, where N sub P is the number of passes, and it's calculated using Miner's rule, which is a way to estimate fatigue life when you have varying amounts of maximum stress. It sums up the damage to estimate fatigue life. So that rule is used to sum up the damage at the small sheave and large sheave ends of the tight side. And so you see in that equation, you've got the K value, which is the durability parameter from table 1717. For each belt, you can see the K values and the B values. And so the number of passes can be calculated. And from the number of passes and pitch length of the belt and the speed, you can derive the lifetime and number of hours. For our example, we had a tight side tension of 64.4. Then for the B-type belt, the K sub B parameter is 576 divided by 7.4 inches. That's 64.4 plus 77.8. So that's 142.2 pounds force. That's a pretty high force that's going on the tight side at the location where it intersects the small sheave. And also on the tight side at the large sheave, using the same equation, you have a force of 116.8 pounds force. From that, we can calculate the number of passes using the Miner's rule, and we get the coefficient and the exponent from table 1717. That's 1193 and 10.926 for the B-type belts. Plug that in, we get 11 times 10 to the 9th passes minimum. That's a very high number. We plug that in, and we know that the lifetime is going to be greater than that 11 times 10 to the 9th passes times 113.8 inches per pass. And then we see where that 720 comes from. It comes from 12 inches per feet times 60 minutes per hour. And then we multiply that by our linear speed, which is 3390 feet per minute, and that gives us 46,600 hours.